When you think about hiring someone for a really complex job, you usually have to make this really tough choice.
Oh, absolutely. It's that classic trade-off.
Right. Like you can either hire the brilliant, meticulous scholar who's going to sit at their desk, stroke their chin, and take, 3 days to give you the absolutely perfect answer. Or you hire the lightning fast intern who just acts on gut instinct, gets things done instantly, but makes a ton of mistakes the moment your business process changes even slightly. You can really rarely have both.
Yeah, the old speed versus depth problem. I mean, we tolerate it in human hiring, and we've historically just tolerated it in computer science too, because we assume that deep strategic deliberation just inherently requires time. You can't rush a master chess player, and you can't rush complex computation.
But today, for you, the listener, who wants the absolute cutting-edge knowledge without having to decode a mountain of academic jargon, we're looking at a breakthrough that totally shatters that assumption. We might actually be getting the scholar's brain at the intern's speed. We are doing a deep dive into a brand new state-of-the-art generative AI framework from researchers at Ant Group and USTC.
And the underlying problem this research tackles is something anyone interacting with or building AI right now is feeling acutely. We want our digital assistants to do more than just write polite emails, right?
Right. I mean, the mission for today's deep dive is to explore this new architecture because it finally solves a massive bottleneck in the industry. Like, how do you give an AI agent the ability to do complex, multi-step planning, which is what cognitive scientists call system 2 thinking, but execute it at the lightning fast speed of a gut reaction, which is system 1? And crucially, how do they do it without expensive retraining? So, okay, let's unpack this. Because this method actually allowed a tiny open source AI model to outperform massive models and go toe-to-toe with proprietary giants like GPT-5.
Yeah, to really understand how monumental that is, we need to look under the hood at why current AI agents fail so spectacularly when you ask them to do something complex. We aren't talking about writing a sonnet here. We're talking about long horizon tasks.
Right, multi-step stuff.
Exactly. Imagine asking an AI to book a multi-city flight. Then analyze a database of your company's expenses, and finally execute a scientific workflow based on that data. When a task requires multiple dependent steps, current AI just hits a brick wall.
Because if step 2 completely depends on the output of step 1 and step 1 goes slightly off the rails, well, the whole system just crashes. I mean, if it books the wrong flight on Tuesday, the hotel booking for Wednesday is entirely useless.
Yeah, that highlights the core issue. And currently, software engineers have two pretty flawed ways to try and fix this fragility. The first is called inference-time search. You basically force the AI to pause before it acts. You make it look at all the possible next moves, simulate them into the future, score them, and then pick the best one.
Which is the brilliant scholar taking 3 days. I mean, it works, but the latency is massive. It takes way too long to compute. Plus, the token cost is astronomical. And, for anyone listening who might be newer to the terminology, tokens are essentially the basic units of AI thought or computation. Every word it reads and every word it generates costs tokens, and tokens cost money and time.
Right.
Nobody wants a customer service bot that burns through 10,000 tokens and takes 4 minutes just to reply to a simple message.
Exactly. So, to avoid that massive inference time cost, developers try the alternative, which is supervised fine-tuning. They take all those complex reasoning patterns, thousands of successful workflows, and they try to bake them directly into the model's parameters.
Yeah.
They literally retrain the neural network to just memorize how to do the task.
Okay, let me jump in here. So is this basically the difference between cramming for a specific test versus actually learning how to study? Like, if you just memorize the specific answers on the flashcards, you're going to fail the moment the teacher changes the phrasing of the question.
Yeah, that captures the phenomenon perfectly. The researchers refer to this as parametric rigidity. So the software API updates its schema slightly. Say, it now requires a 12-digit user ID instead of a 10-digit. Fine-tuned model just breaks.
Because it was hard-coded for the old way.
Right. And retraining it to learn the new way is incredibly expensive. Plus, there's also the risk of catastrophic forgetting, where the AI suddenly forgets how to do a perfectly good old task because you forced it to learn a new one.
Even the newer memory-based agents that try to save past successful runs suffer from this, right? Like, if they try to pull up a past success, they suffer from contextual rigidity. They memorize raw, rigid trajectories. If the exact restaurant name or the specific date isn't what they remember from their training, they just freeze. They're essentially trying to replay a recorded macro, and the moment a new pop-up appears on the screen, the macro clicks the wrong thing.
What's fascinating here is how the researchers looked to cognitive science for a way out of this trap, specifically the dual process theory of cognition. So humans have system one, which is our fast, reactive, instinctive thinking like slamming on the brakes when you see a red light.
Sure.
And we have system two, our slow, deliberate, analytical thinking like parallel parking in a tight space. This paper proposes we physically separate these two phases in the AI's architecture.
So wait, if doing this live in real time is too slow and baking it into the model's parameters is too rigid, where does the reasoning actually happen? Do they just force it to pre-compute all this strategy?
They move the heavy lifting completely offline. They use a technique called Monte Carlo tree search, or MCTS. Traditionally, AI uses MCTS live during a task to search through a branching tree of possible moves.
Right, like a computer playing chess.
Exactly. Calculating every possible move and counter move while the timer ticks down. But here, they use MCTS entirely offline as a high-fidelity data generator.
So it's practicing in the dark.
Yeah, precisely. When the servers aren't busy, the AI is extensively exploring its environment. It's trying different paths, failing, hitting dead ends, succeeding, and mapping out the optimal reasoning trajectories. And the user never has to wait on the other end because it's not happening live.
Okay, here's where it gets really interesting, because they didn't just let the AI click around randomly like a Roomba bumping into walls. They injected these metacognitive operators into this search tree. Specifically, they gave the AI two internal actions it can take called plan and reflect.
And those operators act as internal cognitive scaffolds. They aren't external tools like, search the web or query database. They're instructions on how to think.
So the plan operator forces the AI to break down a big task logically before it takes its first external action, effectively pruning away dead ends before it even walks down them.
Yes, exactly.
And reflect is triggered when a step actually fails. Let's say the AI tries to book a flight and the airline's API returns a weird error message. Instead of just crashing and giving up, the reflect operator forces the AI to analyze the error message and brainstorm alternative recovery paths. It might say, okay, the API rate limit was exceeded. I should pause for 10 seconds or try a different booking service.
It operates much like a chess grandmaster, running through millions of what-if scenarios in their head the night before a match, rather than trying to invent a strategy during the ticking clock of the tournament. They are pre-computing the logic of recovery. And we really see how effective this is when looking at the raw data generated during this offline search. It creates a very specific pattern, which the paper calls a deep but narrow exploration.
Deep but narrow, so it's not searching everywhere.
Right. The branching factor, which is the number of different options the AI entertains at each step, is incredibly low, around 1.3. But the depth of the search regularly exceeds 11 steps.
Wait, a branching factor of 1.3? That means it's not just blindly guessing everything. Like, instead of standing in a hallway and opening 50 different doors to see what's inside, the AI is walking down a hallway with only one or two highly probable doors. It completely ignores the rest.
Exactly. The reward function they build strictly filters out failed trajectories. Because of those metacognitive operators, the AI is only mapping out verified, highly confident paths of reasoning. It is efficiently hunting for verifiable logic, rather than brute forcing every single combination.
Okay, I follow the offline practice. The AI has spent the night generating all these massive, highly accurate data trails of successful tasks. But if it just memorizes these exact practice runs, won't it just suffer from that contextual rigidity we talked about earlier? Like, if it practiced booking a flight to Paris for John Doe, how does that help when I ask it to book a train to Tokyo for Jane Smith? Saving practice runs isn't enough to make the memories reusable.
Yeah, that brings us to the core genius of this architecture, the state goal action extractor, or the SGA extractor. The system does not save the raw text of the practice run. It distills those massive trajectories into fundamental building blocks, which they call atoms.
Like the atomic structure of reasoning.
Yeah. They utilize a process called schema-guided abstraction. Essentially, the system isolates the underlying causal logic of an action and strips away all the surface-level, domain-specific noise.
To make this concrete for you listening, there is a brilliant specific example buried in the appendix of the paper. Let's say during its offline practice, the AI successfully handled a complex prompt where a user asked, "Find me some cartoons from '94." If it just memorized that raw text, it would only be good at finding 1994 cartoons. But instead, the SGA extractor uses a technique called delexicalization.
Right. It removes the specific lexicon, the vocabulary that ties it to one specific event.
Exactly. It extracts the underlying logic into a templated atom. It literally erases the word cartoons and replaces it with a symbolic slot called GNRA. It erases the number 94 and replaces it with year. So the memory it actually saves to the library just says, when the goal is to filter entities and the state requires temporal and genre constraints, you need a genre and a year to execute a wiki search.
And if we connect this to the bigger picture, this abstraction cures what the researchers call lexical overfitting. The AI is no longer memorizing specific data, it is capturing the reusable protocol. I mean, a refund operation for a customer uses the exact same causal logic whether the user is John Doe or Jane Smith. By turning these specific runs into a composable algebra of reasoning skills, the compression rate becomes staggering.
Yeah, I saw that in the benchmarking data. A 6.9x compression rate. The researchers took 10,685 raw, distinct actions from their offline practice and distilled them down into just 1,560 reusable logic atoms.
Which tells us something profound about problem solving, right? Even across vastly different tasks, the underlying causal logic of how we solve problems is remarkably repetitive. You don't need millions of unique templates. You just need the core atomic structures of reasoning to navigate almost any situation.
Okay, so phase one is complete. The AI has built this perfectly compressed library of 1,560 abstract reasoning atoms. It knows the fundamental laws of problem solving. But now we hit phase two, the online phase. A user sits down, asks a brand new, never-before-seen question, and expects an instant answer. How does it actually tap into that knowledge library in real time?
Well, it shifts gears completely. It stops being the slow, deliberative scholar and becomes the fast, reactive intern. The framework introduces a lightweight retrieve, inject, generate pipeline. When your new prompt comes in, the AI acts as a reactive executor. It searches its library and fetches the most relevant abstract atoms, treating them not as strict commands, but as soft hints for how to proceed.
Okay, I have to push back here, though. If the AI is just pulling up abstract templates from a library, what stops it from hallucinating? What stops it from grabbing a template that requires a flight TID when the user's prompt only gave it a restaurant name? Couldn't it just confidently hallucinate an entirely unexecutable plan because the template told it needs a flight ID?
That is a great question, and that vulnerability is precisely why the retrieval mechanism is so heavily engineered. They don't just use semantic retrieval. Semantic retrieval is how most AI search works, looking for templates that have a similar meaning or a similar linguistic vibe. Instead, they built a hybrid symbolic semantic retrieval mechanism.
Hybrid. So it's looking at the meaning, but it's also looking at something else.
Yeah, it scores potential atoms on semantic similarity, but it also forces them through a strict symbolic feasibility gate. The system actively looks at its current state, meaning what factual information it actually holds in its short-term memory right now, and it strictly penalizes and filters out any atoms if the prerequisite symbolic slots aren't present.
Oh, wow. So it literally checks its pockets. It says, this template looks great. It's highly relevant to the user's question, but the template strictly requires a flight ID to execute, and I don't have a flight ID in my current context. Discard.
To use an analogy, semantic retrieval is like browsing through a cookbook and finding a recipe that matches the vibe of what you want to eat. Symbolic retrieval is opening your fridge and checking if you actually have the specific ingredients required before you even start cooking. It acts as a logical safety net against hallucination. If you remove this symbolic constraint, the paper shows the AI's performance plummets because it starts trying to invoke tools without the required arguments.
And once it safely retrieves the correct executable abstract hint, the decision maker takes over. It maps that abstract hint-like year and genre to the concrete details of the user's actual live prompt, say, 2024 and sci-fi. It grounds the abstract logic into reality and executes the action instantly.
Right. No inference-time search required, no generating thousands of tokens to simulate future patterns live. It just retrieves the pre-verified logic and acts.
So what does this all mean? We've seen the architecture. You have offline deep practice distilled into reusable atoms, followed by online lightning-fast retrieval with strict safety gates. But does this complex two-phase system actually perform better in the real world?
The efficiency gains alone restructure the economics of AI. By shifting the heavy lifting offline, the system reduced token consumption by 76%.
Wait, 76%? That is a massive cost saving for any developer.
Yeah, they saved roughly 2,080 tokens per task compared to baselines that use heavy inference time reasoning. The AI gets System 2 strategic depth at System 1 inference costs.
And the performance benchmarks back this up. It's a true David versus Goliath story. They took an OpenWeight's 8 billion parameter model, which is tiny in the AI world, basically a lightweight model you could run locally on your laptop, and they equipped it with SGA-MCTS.
And when you look at the raw outputs, that 8B model saw a 13.86% absolute improvement. Didn't just get slightly better, it matched, and in some complex cases beat, a 32B model that was operating without this framework.
It punched 4 times above its weight class just by having access to good logic atoms.
And it scales beautifully, too. When they applied the system to the 32B model, it hit a 51.09% success rate on complex planning benchmarks. This effectively closed the performance gap with proprietary massive models like GPT-5, which sits at around 55.13%.
And on one specific benchmark, the BFCL-V3, which tests multi-turn dialogue state tracking, the 32B model with SGA actually beat GPT-5, 54.20% to 51.68%, a completely training-free method allowing an open-weights model to dethrone a proprietary giant.
Yeah, beyond just the raw score, the most impressive takeaway is the system's resilience. They tested it on long-horizon tasks, which are tasks requiring more than 4 dependent hops to complete.
This is where things usually fall apart, right? Because of how AI models generate text.
Exactly. And to understand this, you have to understand autoregressive models. Most modern AI models are autoregressive, meaning they generate answers one single word or token at a time based entirely on the previous words in their context window. And the context window is their short-term workspace.
Right, so it guesses the next word based on the sentence it just wrote.
Which means if it makes a slight error in reasoning in step 1, it assumes that error is absolute truth when it generates step 2. A small hallucination snowballs. It's called cascading hallucination drift. On these hard tasks, standard methods absolutely collapsed, dropping to a dismal 15.38% success rate because the errors just piled up.
Ouch, 15.38%.
But SGA-MCTS stayed remarkably robust at a 61.54% success rate.
Wow. How does it survive the drift, though? How does it avoid building a house on a foundation of sand?
Because the retrieved atoms act as logic checkpoints. Instead of relying purely on a volatile context window that gets messier with every new word generated, the agent regrounds its logic at every single hop, using a validated delexicalized schema from its library. It effectively resets uncertainty to 0 before making its next move.
It's like having a map and actively checking your compass at every single crossroad, instead of just walking deep into the woods and blindly hoping your initial heading was right. And they also tested this resilience on out-of-distribution tasks, right? Tasks with entirely unseen tools.
Yeah, they utilized what they call the tool familiarity score. They compared SGA-MCTS to traditional memory systems like LangMem, which retrieve raw past trajectories. When the tools were familiar, both did well. But when the tool familiarity score dropped, meaning the environment and the software APIs were totally novel, the traditional memory systems failed due to that contextual rigidity we mentioned earlier.
Because they were desperately looking for the specific buttons they pressed last time, and those buttons didn't exist in the new software.
Exactly. But the SGA framework crushed them because it wasn't looking for specific buttons. It was looking at the underlying logic. It proved that it could transfer its abstract reasoning to semantically distinct, totally alien tool ecosystems.
This is a massive paradigm shift. For you listening, we are essentially witnessing a shift away from the brute force era of AI. We don't necessarily need to build models with trillions of expensive parameters to solve hard problems anymore. Instead, we can use highly efficient, retrievable logic to allow smaller, cheaper models to punch way above their weight class. It makes high intelligence planning scalable and, crucially, feasible in real time.
This does raise an important question, though, and it's the limitation the researchers acknowledge at the very end of the paper. Currently, this entire offline logic library, the 1,560 atoms, is built using seed questions provided by human engineers. Humans have to tell the AI what specific problems to practice offline.
Right, the AI can only explore the boundaries of the sandbox we put it in. If we don't ask it to practice booking flights, it won't discover the logic of booking flights.
But what happens when we integrate active learning? What if we remove the human bottleneck entirely and allow the AI to autonomously propose its own tasks to explore during its offline downtime?
Oh, wow. So when the server isn't busy processing our requests, the AI just starts inventing wildly complex, hypothetical problems for itself to solve, and then distills its own solutions into new logic atoms.
Yeah, we're looking at a future where an AI doesn't just learn from human data. By actively architecting its own underlying laws of logic, it could map out the fundamental reasoning required for environments and software systems we haven't even discovered or built yet. It wouldn't just be practicing. It would be proactively expanding the frontiers of its own cognition.
That is wild. It's not just the brilliant scholar or the lightning-fast intern anymore. It's an intern who goes home at night, writes the definitive textbook on how to run the entire company, and comes back the next day operating like a visionary CEO. Something for you to mull over.